All right, everybody. We are on to our last topic in the course. It's going to be pretty exciting, but we're actually going to make a little change to what we've done. So far, everything that we've done has been single variable statistics. You know, we had one thing to measure, like an IQ score or the difference between the values of books or the proportion of people who are going to vote a particular way or something like that. We were only ever measuring one variable. But in reality, a lot of statistics or a lot of data has associations between variables. So you might have two variables that are happening instead of just one. So to get us going, there we are. To get us going, let's look at an example here. So two-dimensional data, each observation has two numerical values. And the question that's underlying what we're going to do today is there an association, or in other words, is there a function that describes the relationship between the two variables? So let's take, for example, a very classic data set. This is the old faithful data. For every single one eruption, there are two measurements that were made in this data set. The time between eruptions, that was the time from the last one to the one that you're actually measuring now, and then the length of the eruption. And the most natural way to actually visualize that is to actually plot them as a scatter plot. So I've got wait time here in minutes between eruptions and the length of the eruption itself in minutes on the y-axis. So every single variable every single observation has two variables, wait time and eruption. Well, let's just kind of look at how we build this data. Or how we build plots like that and what we can do with it. What are the natural questions? So go ahead and grab this data from the Google Sheet linked below. Right? If I highlight all the data, so that was Control A to highlight all the data, and then go to Insert a Chart. Now it gives me kind of a nonsensical chart to begin with. Google Sheets tries its best, but it doesn't actually always succeed. What I really want is a scatter plot, which was thankfully suggested here. So I'm going to click on scatter plot. And if you don't like that one, you can of course scroll down and find scatter plot here. Right? And it looks like there is kind of a natural association as the length of time between eruptions goes up, the length of the eruption increases. Now, if you think about that, we're talking about water that's kind of boiling underneath the surface. And if we're boiling it for longer and longer and longer, it's going to take longer to erupt. That kind of makes sense. But what is the nature of the actual association? So if I double click on one of the points, I can do some really naive things in any spreadsheet software. And I can come down here and put a trend line on. Right, so I put the trend line on, that's perfectly fine. I can make it a little bit thicker so we can maybe see it better. So there's our trend line. Well, this tells us kind of, okay, maybe we've got a slope. Let's see here. Let's actually make the label the equation itself. So now I have like a slope and an intercept. So y equals mx plus v is kind of our association. And I can see, well, for every minute maybe that I wait longer, I get about 7/100ths of a minute longer in the eruption time. And I can just start clicking buttons here in the spreadsheet and it can tell me what the association is, but it's meaningless unless we actually do a little bit of statistics here. So let's kind of see how we as statisticians measure some of these associations. So if I come back into here, if I want to measure the quality of a linear association, I've got this nice little tool that lets me do this. Now this tool is just a toy, right? It's not anything fancy, but it's supposed to give us the idea of how the association, the quality of the association between the two variables is really measured. So in this little toy here, which you can find linked below, I can put, let's say like, I'm gonna say like 4 points in here. All right, so I've got 4 points. And I can pick the points up and move them around if I wanted to, whatever. I can show the linear regression line, or what's called the least squares line. So what this is the computer's estimate for what is the best linear association between the data points that I have. And of course, if I go down below, let's see, it looks like I can have negative associations. Notice the negative sign here. Right? I can have quite weak associations where the points are a long ways away from the line, or I can have quite strong associations where the points are almost right on the line. Okay, but how is it measuring this? Okay, so what I'm going to do is I'm going to show what's called the residuals. The residual is the distance from the point to the line, and the goal of linear regression statistics is to find the line that minimizes the sum of the squares of the residuals, which we'll actually play with here in just a little bit. All right, so now if I add a whole bunch more points, notice that as I add more points, the line doesn't change by much. And I can get a good association for what's actually happening within my data set, what sort of association I have within my data. So the goal statistically is to take your data and find the line, the blue one here, or the blue one going through this, that best approximates the data. And what we mean by best approximation is the one that minimizes the sum of the squares of these residuals. Now, the sum of the squares of the residuals is one form of measurement. We actually turn this into what's called a correlation coefficient. The correlation coefficient, which is abbreviated with the letter R, is either 1 or -1 if you have a perfect fit. So like I've got a perfect fit of 1 here, 1 here, 1 here. Those are all ones with positive slope. Or -1 here, -1 here, -1 here. And here, those are all ones with negative slope. And now if the sign is positive, then there's a positive association. So like this one, I've got a correlation coefficient of 0.8. Right? So I could draw a line with a positive slope going through this one. Correlation of 0.4, I've got a positive slope going through this one, but it's fairly weak. Correlation coefficient of -0.4, I would draw a line with a negative slope through this one. Correlation coefficient of -0.8, I would draw a line with a negative slope through this one, and it's kind of strong. And then a correlation coefficient of 0 really just means there's no association whatsoever, right? As one variable changes, the other variable doesn't change at all. And if I draw any of these, you notice that there's really no association between what happens in the horizontal direction and in the vertical direction in terms of a linear relationship. Now, the R squared, the coefficient of determination, literally just the square of the correlation coefficient, is another way to tell us how good the fit is. Oops, those should be squares right there. I'll fix those on the slides. So if the R squared is 1, it's a perfect fit. If it's 0, there's no fit. So notice over here, I've got a cloud of data. And there's no fit whatsoever. I mean, you can't tell that there's a relationship between these X's and Y's. Whereas an R squared of 0.9, now notice I squared, so the negative sign is gone. And this is a pretty good fit. A 0.83, this is also a pretty darn good fit. Whereas this one, there's really no linear association between the horizontal and the vertical variables. And so the R squared value is really, really small. Now, the advantage to the coefficient of determination, the way we measure how good this fit is that it tells us the percent of variation in the Y explained by changes in the X value. Right? And so we're going to go through and we're going to look at lots of data sets that that we can actually get specific values for these things. But over here in our Old Faithful data, I have a coefficient of determination, an R squared of 0.811. So that means I've got a pretty strong fit, and that for every minute we change, here we go, for every minute, oh, wait a minute. I was about to say that wrong. Let's try this one more time. The R squared value of 0.811 tells us that 81.1% of the variation in the eruption time is explained by changes in the wait time. So if I know how much time has elapsed between eruptions, I have a pretty darn good sense of how long the next eruption is going to be. 81% of the variation that I see in this eruption time is explained by how much time I wait. Okay, in the next videos, we're going to look at a few more data sets. We're going to play with these two variable associations throughout the rest of this lesson.